Good evening, everybody. My name is Jim Westmoreland. I want to welcome you to the 2013 PSS Speaker Series this evening. We're certainly pleased that you're here. We're certainly pleased that we've got our panelists here with us this evening. We're looking forward to another great presentation and panel session, and specifically around technologies. Just so you'll know, I'm the current Entry Advisory Council Chair. We had our meeting this afternoon, and we talked about all the good work that's going on here at Entry and NC State specifically. Wanted to recognize Nagi, wanted to recognize all the members of the staff. If you would just stand up for us a minute, be recognized. Let's give them a round of applause. Entry and NC State, I think, continue to exceed all of our expectations in terms of the work that they're doing. It's always interesting to us as advisory council members to hear about the good work that's going on at NC State through Entry. Tonight's topic, again, is transportation technologies for the 21st century, a peek at highway, rail, and aviation modes. I think some of you may know me from my past role with the North Carolina DOT, where I served as the Deputy Secretary for Transportation over all of the different multimodal modes for the department. Have recently shifted gears. I'm now with the City of Greensville as a Deputy City Manager. Anyway, I can tell you from the perspective of the work that I did at the Department of Transportation, specifically as it relates to the different modes and some of the technologies that you'll hear about tonight, it's exciting. I was telling our speaker here, John Gilligan, just a minute ago, as I was sitting there this afternoon and sort of thinking about and reflecting upon some of the technology I had provided to me as a young undergraduate at NC State back in 1983. It's just amazing to me how things have changed. I know when I came to NC State, we had a computer lab. I think we had graduated from the old punch card system. We were finally with a computer lab. But just the lack of technology, the things that we all take for granted today is pretty amazing. Again, I think we're going to have a good time tonight. I think what I would encourage you to do is to first of all listen. I think you'll learn a lot from each one of our speakers and panelists this evening. We will have a Q&A session afterwards, and I think so. Be thinking about your questions. If you're like me, I have to write my questions down as I hear them, because sometimes I'll get multiple questions going on in my head and get confused with things. But anyway, we're looking forward to the panel session tonight and your participation. At this time, I want to introduce Dr. John Gilligan. Dr. John Gilligan is Professor of Nuclear Engineering at North Carolina State University and Senior Advisor to the Dean of Engineering. We're pleased to have you with us this evening. Dr. Gilligan is a former University Vice Chancellor for Research and Graduate Studies at North Carolina State University. During his 6 years in the tenure, research expenditures at NC State University grew to over $360 million per year, with 400 doctoral graduates per year for the first time. Dr. Gilligan received his bachelor's degree in engineering from Purdue University, master's and doctoral degree in nuclear engineering from the University of Michigan. He has served on the faculty in the University of Illinois, held research positions at Princeton University, and how do you pronounce that? Agron?
Oh, Argonne.
Argonne
National Lab.
Argonne National Lab. He's held many leadership posts. I was talking to him earlier. He's been with NC State now for 30 years. 30 plus years. Anyway, we're pleased to have him with us tonight. If you would, please come and provide us with a few remarks. We'd appreciate
Well, thank you, Jim. I appreciate it very much, and Nagi too, and all of Entry. And welcome from NC State University and the College of Engineering on behalf of our dean, who's out of town tonight, and brings his wishes of welcome too for you in this important occasion. Thank you for being here on Centennial Campus in the Monteith building. This was one of the first research buildings on this campus in 1996. It's a very important building, by the way, historical in that sense. Now, I don't know if you've had a chance to visit Centennial Campus since you've been here, but it's huge. It's 1,500 acres. I would encourage you to spend some time here on Centennial. It's a world-class model for the kind of research that we do. About 3/4 of the College of Engineering is now on Centennial Campus, including a good chunk of civil engineering, which is over here, right, in the Constructed Facilities Laboratory. We have 9,000 students in the College of Engineering here, making it the 4th largest in the United States. It's a huge complex. $150 million in research expenditures now in the College of Engineering. and we're the only campus in the U.S. to have 2 NSF engineering research centers that are currently operating. It's across the entire United States. So we're very proud of that research expertise and excellence that we have. We also have a DOE national hub in modeling of nuclear reactor, light water reactor simulation. Very proud of that as well. Now, when you come out here to Centennial Campus, what you'll see is the new Hunt Library. I would encourage you to go see that new Hunt Library. It's just incredible. Just came online in the last couple of months. You feel like you're walking into a museum, an art museum, when you walk in there, and then the technology is just incredible when you see exactly how books are retrieved with the BookBot, which is a kind of a robot that goes, selects books, and a very impressive kind of technology to us engineers. The new golf course clubhouse is being built right now. There's new science alliance building going up over here that will house some of our departments. There's a new 1,200-bed dormitory for graduate students going up on the engineering quad, which is just up the hill here. Very proud of that. New set of apartments, new set of condos, a new executive hotel and conference center that's just being developed right now in negotiations. So we're very proud of Centennial Campus and the role that the College of Engineering plays here. Also very proud of our students at NC State in the College of Engineering. I just got the statistics this morning. The average SAT of the students coming into the College of Engineering is 1,350. That is very, very high. For those that kind of don't remember those numbers, but that's incredibly high. I probably did not get in as a freshman here at NC State. Probably some of our faculty, other faculty, the same way. In other words, 75% of the students that we admit into the College of Engineering are in the top 10% of their class. 75% are in the top. So it's a whole different level when those students come in and introduced to the technology that we have here at NC State. So we're very pleased to see support for the TFF and the kind of work that it does. The special speaker series tonight is very appropriate, talking about 21st century peak at the highway, rail, and aviation modes. I want to thank George List for putting together the program and helping to do that and being the moderator tonight, and of course the speakers for being here and providing your expertise to us. I think that's incredible. The students that are here, I think you're going to have a treat, and we certainly thank you again for attending and hope that you have a great evening. Thank you very much for being here.
Thank you.
My name is George List. I'm a faculty member in civil construction and environmental engineering here. We have a really exciting panel lined up for you tonight. A mentor of mine, Aaron Gilman, who does a lot of work in the aviation industry, used to talk extensively about how technological innovation makes it possible to do things that you couldn't do before. And we have 3 people here who are going to talk to us about that issue in the context of railroad, in the context of aviation, and in the context of highways. And without further ado, I'm going to introduce the first one of those. I've had the pleasure of meeting David within the past couple of years. He is an NC State alum, and he is currently Regional Vice President of Operations at Union Pacific Railroad, and before that he was a Vice President of Engineering. He's had a lot of experience both in the freight side as well as the passenger side of running a railroad, and I'm sure he's going to have a lot to talk to us about insofar as technology and its influence on the way the railroads operate. David?
All right, well, thank you, George. Get this here fired up. All right, well, again, thank you, George. It's great to be back. It's great to be back in my home state. It's great to be back at my alma mater. I actually left here 30 years ago, maybe about when you got here. And yeah, I had hair. And I did had to punch those cards. Oh, yeah, you had a deck, and you better not drop them. That's that technology we call rubber bands were very important back then. I'm going to talk to you tonight about something that's I've spent a lot of my professional career very close to. Is I have a real passion for R&D. I actually led the R&D group for UP for 5 or 6 years in trying to make our infrastructure much stronger and more reliable. I'm going to spend a lot of time tonight, and I'm going to go through this very, very quickly. There's a lot of content here. I don't want to get bogged down, so if you see something you want to ask about, we'll save that for the panel discussion later on. Really talking points. I'm going to lead off with talk about U.S. research, how we compare in research funding with the rest of the other modes, and how we compare in research funding with other countries. I'm going to talk about TTCI, which is our country's, the AAR's research facility for rail technology out in the desert in Pueblo, Colorado. And they're only going to talk about the technology in details, really break it down into 3 buckets. I'm going to talk about recent breakthroughs, and that's really the last 15-year type stuff that, quite frankly, we're leveraging in a great way to produce good results as a Class 1 railroad. We'll talk about emerging technology, and we'll talk about 4 or 5 technologies that are really just on the brink of really getting some teeth into them, and ones that are very needed in our industry. You're going to see a lot of UP on this presentation, but the truth of the matter is this technology is used on all the Class 1s for the most part. So, railroad research, about $800 million spent on highways. You can see that we spend about $48 million on rail. That chart's, at least it's an odd chart on what I'm looking there. Maybe it's better here. Spend about $48 million, both the industry and the FRA combined to about $50 million a year in research. And you can see what Germany does by itself, and it's about a factor of 6 below what the EU does. Obviously, it's about a factor of 3 under what Japan does. So we've got limited funds, and we've got to make the most of them. The American Association of Railroads, the AAR. The AAR is made up of most of the Class 1 railroads, and the AAR actually funds a group in the desert in Pueblo, Colorado, called TTCI, the Transportation Technology Center Incorporated. That's a facility that's actually leased from the FRA. The AA operates it, so they do research for the industry, for the Class 1 owners of the AAR, but they also do private research as well. So talking a little bit about what that facility is. You see the administrative building there, but there's 7 different tracks that, I'm not sure how many acres this is, but this is probably 20, 30 square miles of desert just east of Pueblo, Colorado. Probably the neatest thing they do out there, most repetitive thing they do out there, they have a heavy axle load loop that's about 2.3 miles long, and they continually run a heavy axle load train around in a circle this way, then around in a circle that way every day, trying to test various track components. And I'll talk to those a little bit here in just a minute. But they do a lot of private work. The Japanese railroad does come over and do some testing in the desert. European entities do come over and do testing here. It's very well known. I would put it up against anybody in the world. So, we're going to transition to recent breakthroughs. And at the top of that list, which really has driven a lot of productivity for the freight side of the world, is called distributed power. And nothing more than a remote control locomotive that can be dispersed anywhere back in the train, mid-train, end of train. So what that's done is allowed us to effectively double the size of our trains with the same overhead, other than the locomotive. So we've got one engineer, one conductor, and literally you can pull an infinite train. You can distribute. The only thing that controls the length of train really is how far a locomotive is one from the other as far as communication range. We recently ran a 16,000-foot train from Dallas to Los Angeles, just to prove we could. We can. Bad thing is, when something bad does happen, you got 3 miles of something sewed up. So we're not going to do that much anymore. We run a lot of 2-mile-long trains today. So DP has been a tremendous benefit for especially UP. We run about 250 trains a day that have distributed power at various places in it. Wayside detection. Obviously, safety is huge with the railroad industry. We're using different technologies today to try to understand what kind of defect conditions the rolling stock of the locomotives may have. This came into a very big way back in the mid-'90s with the first wheel impact load detectors. Wheels are slid flat for all the wrong reasons, but for braking issues, or a wheel locks up and slides for several hundred feet, it can create an out-of-round wheel, and it just pounds the railroad for the next thousands and thousands of miles. We now have a way to find it and get them out of the fleet. Other things like laser-based wheel detection, we're actually able to measure every wheel passing with lasers to understand when they are reaching the wear threshold set by our regulator, the FRA. We're listening for bearings as they begin to fail. A couple of more wayside detection technologies. We actually use ultrasonics, and that top photo there is actually a trolley system that we run a train, a 130-car train, through a building, and we actually engage the wheel with the trolley system with ultrasonics, and it follows that for a couple of revolutions to look for internal defects in the wheel. We have way too many train accidents today that the wheel blows up from the inside out. Very difficult to find with traditional means. Other types of machine vision that I'll talk about here in a little bit, what you see in the bottom right, what we call the railroad industry a hot box. That is a fail bearing. That is a bearing that's really been burned off. A few track components here. Obviously, we're going more and more to concrete track in special environments. You look at that center, that is what we call a movable point frog. That's technology that came over from Europe back in the mid-'90s. It's been used over there for a number of decades. We had to harden it here for our axle loads here in the country. Frogs are very high where the two tracks cross. There's a gap. The wheel's unsupported. It's a very high maintenance item for this, and movable point frogs have taken a lot of maintenance cost out. Rail, we buy most of our rail from Japan. We believe it's the very best rail produced anywhere in the world, and rail life pretty much has doubled in our most demanding environments really in the last 20 years. So we talked about concrete ties. If I can get this to work, the top left here is what we call our track renewal train. Our track renewal train is where you take wood track, it completely takes out all the wood ties, all the old rail, and will install brand new concrete ties, lay them to the right spacing, put the rail down, flip it up, heat it to the right temperature, and we can do it 2 miles a day with this machine. This is I believe is the best machine in the world right now. We've had it for about 5 or 6 years. Another big breakthrough in our maintenance business was how we ballast the railroad. It used to be a very, very dirty job, a tough job. We'd have people walking actually beside the train for 10, 12 miles a day, opening and closing doors. This is a fully GPS-enabled train. There is nobody that accompanies this train. This is a 40-car train in the middle of the night, all the doors open by GPS, pre-programmed to where ballast needs to be. It's really been one of those breakthroughs. It's enabled us to improve productivity as well as to drive out risk. Positive train control. Everybody's heard of that, PTC. Positive train control emerged because of one accident back in 2008 in Chatsworth, California. If you recall, a Metrolink locomotive engineer at a station left the station, was distracted by a text message, completely ran the signal, went around a curve in a tunnel, and met one of our trains head on. 25 people dead. Because of that trigger, Congress enacted the Rail Safety Improvement Act that said all railroads will have PTC installed on all tracks that meet a certain criteria by the end of 2015. That's been a very tall order. basically how it works. Every locomotive actually has got technology on board it. It ties into GPS, so the system knows where the locomotive is. It knows the terrain. It knows what it's pulling, so it can calculate a braking curve, and it will not allow it to get by a signal that doesn't have its permission to proceed. It'll be very difficult to make it by 2015 just because of various approvals that we don't have yet from the technology side. But we've got 400 or 500 people working on that just on our railroad alone. Our railroad is very heavy in inspection labor, and we're looking at various machine vision technologies, whether it's mobile or whether it's wayside, to look at track and rolling stock. One of those new installations. This will be the very first one anywhere in the U.S. that we're building right now in North Platte. Looking at 360 degrees all the way around the rail car, looking it up, and the eventual intent is to supplement our inspections and maybe replace the way we inspect now. A lot of times we're out there at 2 o'clock in the morning with a flashlight and a snowstorm trying to find a defect, and sometimes we're not as good as we need to be at it. This works hopefully much more reliable than that. So we're looking forward to the safety that this system brings to us. Another developing technology is rail flaw. Broken rails are still a leading cause of train accidents in the U.S. What you see there is a fatigue rail flaw. Very difficult to find under certain surface conditions. We use ultrasonics. You see all the angles there on the bottom right that we currently induce sound. We still miss a lot. We're looking for different ways to hit the rail with sound, maybe through lasers or phased arrays to better cover the perimeter rail to reduce broken rails. Track buckles. We don't have clickety-clack rail in the obviously. We're welded rail. With welded rail comes inherent risk of not controlling compressive stresses in the rail when it gets hot. We need a way to go down the railroad at 50, 60, 70 mile per hour and figure out what that stress is, what those compressive stresses are in the rail. There's various technologies that we use. They're all fixed. Just got to know where you think you may have a problem before you can confirm it, and that's another opportunity that we really need to some smart minds on. Remote track assessment, I'm not going to talk a lot about this. Currently, most of our assessment today is twice a year with very, very sophisticated electronics, or it's twice a week with vision and a vehicle that rides on the rail. We want to combine both that frequency and have a fleet of locomotives, 300-400 locomotives that can all inspect the rail every time it goes across. This is technology that the industry is working on as well. You heard about the tragedy down in Texas last night. If you remember, about 7 or 8 years ago down in Graniteville, South Carolina, there was a main track switch that was left open accidentally in a car chlorine. It was an accident that involved a breach of a car chlorine, and a very bad thing happened. We're looking for technology outside of PTC that we can see switch position in what we call dark territory. So non-signalized track, a switch can be thrown. It's sitting out there waiting for a train to hit it at 50 miles per hour and not know it's in the wrong position, that somebody accidentally left it. So we're looking for some low-cost technology that can help us with this as well. PTC will fix this where PTC is installed, but PTC is only going to go about maybe 55 or 60% of the footprint of our network. LNG, obviously, natural gas prices of the railroads, who are the second largest consumer of diesel fuel in the country behind the U.S. Navy. The BNSF is number 2, and the UP is number 3. We're looking at how to convert some of our locomotives to natural gas. It's a very active project right now with all the Class 1s. If anybody can tell us how long natural gas prices are going to stay where they are, we will get a lot more interested in it probably than maybe we already are. Okay, and then safety. Grade crossing warning devices, that's the trend of accidents over the last, 30 years? Really 40 years. And you can see that we flattened out. And I'm concerned. I'm concerned that we're having way more grade crossing accidents than obviously we need to be having. There's lots of distractions that are causing them. Everybody knows what those reasons are. concerned about Section 130 money that could be drying up, depending on what happens with the transportation bill. What you see there at that bottom left is 4 quad gates. This is actually on our high-speed rail system, higher speed rail system between Chicago and St. Louis. So 4 quad gates, the route is completely blocked off. You have presence loops to where we know there's no vehicle sitting inside. And actually, in this route, there's actually technology riding on the locomotives to know when there is a vehicle in the foul, and the train actually prepares or approaches the crossing prepared to stop. So this is another area to where we've come a long way, but we've still got a long way to go. That Walmart truck was just struck last week in Sioux City, Iowa, from what we call a short stage crossing. He was stopped at the stoplight and hanging back on the railroad track. Okay, in closing, so U.S. Rail Research, it's very strong. They do quality work. We're surely lagging the rest of the world from a funding perspective. The facility in Pueblo is world-class. FRA does have limited funding. Some of that funding does go to universities. There's 4 or 5 universities that they fund a lot of their research funds to. The AER also has 4 affiliated universities that funds go to. But when you look at the end of the day, some of these technologies have made this industry the safest and the most productive it's ever been. So a lot of you don't see behind the scenes what we're working on. That's just a really quick collage of all those things, and be happy to take questions once everybody's done. Thank you.
David, I think you're right that in many ways all of the technological innovation that goes into the rail industry is basically unseen, because it's already a technology, an operating mode, a mode that operates sort of fairly silently behind most of the activities that we see in daily life. That can't be said for the next speaker. We're all people who ride planes. We all are very much aware of airports and aviation technology, and he's going to talk to us about how things are changing in the aviation world as a result of GPS and lots of other things that have to do with the way that planes navigate through the skies. It's going to be a huge change. We're interested in hearing about it.
Thank you. I'm going to come at this discussion with you through the lens of strategic thinking, and share with you some of the work that's going on in the federal sector and a little bit in the private sector and in the university world as well, to try and discern how to think about the future. My engineering training did not include training in strategic development, strategy execution management. That all I had to learn with the School of Hard Knocks. But the role that I'm involved in these days through my company, Next Gen Aerosciences, predominantly includes supporting federal sector entities and some state entities as well in thinking about the future of aviation. So first, a little bit of kind of what is strategy? Well, strategy is what you have to do at this knife's edge between that which you're assured of on the one side, and that which you do not understand or know about on the other side. So you're going to have to pick a path in the presence of those, that sort of razor's edge, if you will. And one of the challenges to strategy is projecting into the future with numbers that you can turn into investment plans for new airplanes, new airports, new whatever, pilots, everything. And it's not hard at all to do that projection when the future looks like the past. However, in aviation, going to submit today that the future doesn't look at all like the past. I've been flying airplanes since I was 14 years old, which was more than 50 years ago. And I realize now that this passion that brought me this far in my life, passion for aviation, no longer serves the future of aviation. General aviation, as we commonly call it, airplanes built by veteran companies like Cessna, Beechcraft, and Piper, and others, may survive into this future, but I'm not so sure. Forgive me if you're from a Cessna family or a Piper family or a Beech family, but I think you'll understand what I mean. The reason is that you can't draw a straight line from the past into the future in aviation, in many areas, certainly in aviation. The rate of change we're experiencing in the globe is accelerating. If you're a student of Kurzweil and others, you'll have kind of your own translation of what the singularity means in 2029 and things like that, and how it could affect, how these advancements could affect such things as vehicles that can be truly autonomous, whether they're on the ground or in the air, and airspace management practices that can be automated rather than human-centric. My friends in the FAA have reactions that range from gasping in horror to hear about having automation take over, quote unquote, the role of the human. I think that's a long ways away, but I also at the same time I believe we're headed there. And I think when we get there, we're going to be amazed at how fast we actually got there, which is frequently the case. So I'd like to chat you through the big story as I understand it about the future of air travel in the United States. These significant changes that I'm talking about are not just in technology affecting aviation, but they're everything that is happening on the planet that creates the context in which the future of aviation can be crafted. Just take energy, for example. Let's see here. One of these is a pointer. There we go. Energy, for example. I mean, there is the story that we are seeing the rate of change of energy out for energy in increasing in the wrong direction. It's taking us more energy to get the petroleum products in particular out of the ground than it ever has in the past. And that in itself has created dynamics that show up in fuel prices, for example. And so what does that look like over the coming, say, 20 or 30 or 40 years? We need to have a little bit of a picture about that. Demographics. What does the consumer of aviation transportation or automotive or train look like 15 or 20 or 25 years from now? We're already beginning to see changes in the demographic behaviors of consumers of those modal options for transportation. We're seeing, my generation is sometimes referred to as the boomer generation, baby boom generation. There's a younger cohort that sometimes is referred to as the millennials, right, the 20-somethings. And their behaviors, those two groups behave completely differently when it comes to consuming technology, for example. And so we're expecting, in projecting future demand for air travel in particular, that those kind of demographics will play into how the future unfolds. So there's a field of study in that arena. Our firm is involved in computational modeling of demand over the entirety of the national transportation system. While I'm not going to share any results of that modeling today with you, the results of that work for several federal agencies will be published later this year and might be of interest to those of you who have some interest in transportation. The FAA every year publishes a report they call the Terminal Area Forecast. what they try to do is they try to look forward into the future. In this case, it looks forward to about 2035. And they try to project, okay, the demand for consumers and claimants, basically, the revenue passenger miles, and they translate that into numbers of flights, for example, numbers of aircraft. But they've tried to project that. What you're seeing here is that the real demand is the black line. And every year they've done the projection, they've done this little sort of hockey stick thing, and it's been wrong. Something systemic is changing in the way consumption is happening, because this is a case where you're trying to draw a straight line based on historical data into the future, but in fact, the curve goes like this, and all the straight line does is give you the tangent, right? So let me say just a little bit more in my remarks about the context at large for air transportation. My main point is going to be you can't study air transportation in isolation. You have to study it in the presence of all other modes. There is an increasing vacuum in the marketplace. The airlines have figured out, it appears, how to survive financially. It's why those of us who fly these days see airplanes that are full, see fewer flights to a lot of the cities we used to be able to go to conveniently. And that's a trend that's been underway for 10 years and is not apparently going to be reversing anytime soon. And there are increasing values to the solution, because along the way the airlines, as they figured out how to consolidate in order to survive economically, are also thinning out their markets in places that are less served. So you'll see a little bit of that information. I want to say a little bit more about this scheduled air carrier story. This is the number of commercial service airports in the United States. This is the time by year, 1970, 80, 90, 2000, 2010, across the page. And what you see is that back in the 70s and 80s, we had almost 900 commercial service airports in the United States. We have 382 today. And that trend is underway. My friends, one of whom is Aaron Gilman, tell me that this downward trend can't continue. He says, it's going to flatten out. Well, he's been telling me that for about 5 years. So some of us, after a 33-year career at NASA, I decided to get into the world of startups, and I'm on my fourth one, two of which have been successful and two of which I learned a lot from. I encourage you to live that life if it appeals to you at some point in your career, either before or after the career that pays for your children's college education. Well, I was part of the team starting Dayjet Corporation. It was an on-demand per-seat air carrier with a fleet of 28 jets down in Florida. And we served 61 markets. It was based on a new aircraft. It was based on a new technology.
Need to decline that.
That's college. Yeah. A little early.
So it was the first per-seat on-demand air carrier. It relied on new technology for real-time logistics management. First time it had ever been done. Relied on new aircraft. Coupling two startups together is a bad idea, I must say, because after a year of revenue service, on one sad week in September of 2008, AIG, Bear Stearns, and Lehman Brothers, who were in our debt and equity financing wheelhouses, all went away. And that was the end of our dream for that airline. There are others out there who are starting up similar ideas these days now that things are getting better. We're hoping to be of some help to those companies as new airplanes come online that can make that model work even better. Linear Air is still operating. You can see the numbers of airports. We had 61. Linear Air actually has more than 200 now. This is an old chart. SATS Air had about 520. And so my own point is that while the airlines are consolidating to survive, they must do this. They consolidate as air carriers. They consolidate to fewer cities, larger cities, and consolidate to larger aircraft. You must do this. They're leaving a vacuum behind, however, that can be filled someday. Well, be filled with what? General aviation, I suggested at the beginning of my remarks, probably is not as relevant as in the form that we've known it in the past to the future. In other words, how might it be that smaller aircraft and community airports could be useful for public transportation? That's the sort of question that I think we need to be asking. And another way to ask the question, in the context of these kinds of data, let me explain what's on this chart. The vertical axis here, towered general aviation operations. This means an airport with a control tower that has general aviation flight operations. These are numbers of operations per year. These are the years across the bottom, 1960 to 2010. And over here on the right-hand vertical axis is the GDP in fixed-year dollars. And you can see that GDP is rising, and for years, general aviation kind of operations kind of rode along with GDP, but has become uncoupled in a way that we've not seen before. This tells me that something systemic, again, has changed in the way consumers now look at this modal option. And so there are companies who are involved in avionics, in building new aircraft, who are taking a hard look at this situation and saying, there's a market there. How can we serve it? And what does it look like in the future? I'm going to suggest to you that it could look as different as you could imagine in the following form. Airplanes that don't have pilots carrying people to go where they want to go. That's going to happen in your lifetime. Now, the bad thing about predictions is that it's a bit of a fool's errand, right? But the pieces are in place for that to happen. One of the best ways to predict the future is to create it, right? Don't bother with saying what could be. Go out and make it happen. Just do it, as some of the commercials said. Well, we did have programs in the past, and North Carolina State University was involved in a program called Agate that NASA ran back in the 90s. And you can see the effect that Agate had on causing something of a rise, at least an indirect effect on a rise in the consumption, but it wasn't enough. We wanted to make airplanes easier to use, or make them safer, have higher utility. Quite simply wasn't enough. For those of you who have flown in a Cirrus, for example, aircraft, you've seen how amazing the glass cockpit technology is these days compared to the way it was just in the previous generation. So there are changes at work here. Will they move the needle? What does it mean to move the needle? It means tracking with GDP, or plot population of the United States on that other axis. Track with the population. General aviation is not doing that today either. So in our modal work, in our modal analyses, what we're doing is we're trying to understand what will move the needle. We're trying to understand what the consumption behaviors are as a function of geographics, demographics, economics, all of the factors that affect energy prices, GDP, disposable income. And so we include all of those parameters in agent-based models that project demand and demand satisfaction, known as supply, into the future. But for aviation, we need to know what might happen, for example, with bus infrastructure. And so we merge a set of alternative bus infrastructure. You know, you've seen these mega buses, the intercity buses. And I love the ad on the back that says, go to New York from Hampton. I live in Williamsburg, so it's like, go to New York City for $1. And then it says asterisk 50 cents for a carrying charge or something like that. That's right. The first person to buy the ticket gets that, and then there's more tickets or more. But anyway, we had to include what the bus infrastructure. We also needed to include what the rail infrastructure could plausibly look like. And so we do different worlds. We do different scenarios in order to understand under scenario A, which is a combination of this bus and this train, or this bus and this train, and look into the future at what that demand might actually unfold to be. So these are results, as I mentioned, that we'll be publishing later this year on behalf of our government, federal government sponsor. We also include things like population dynamics. There are these sort of expansions into exurbs that are occurring around cities. Atlanta is a classic example where they're talking about, well, if you live on the north side of Atlanta, now the trip to Hartsville has become a very long drive. And in fact, if you're only going to Nashville, it's faster to drive. Well, what does this migration pattern, how does it affect overall transportation consumption? Ground, highway, rail, bus, and air. And we include these kinds of effects as well. One of the clients asked us to include what happens if we have higher water. Well, in the eastern seaboard where I live, in the Norfolk Tidewater area, that's a very deep concern. We have subsidence of land coupled with rising sea levels. And in about 30 years or 50 years, we expect to see somewhere between 1 and 4 or 5 feet of additional tide levels in our area. Will we see those? The folks who study and model those things say yes. Our client wanted to know what happens if airports are affected in places like New Orleans and New York and Norfolk and others to demand for air travel. So we want to know those things too. I've already covered this, so I'm just going to give you these headlines. This is, again, annual commercial operations. What you're seeing is slower growth in scheduled service. You're seeing flight segments that will be longer. This is average flight stage length as a function of year going out into the future, 2030, 2040, well, 2035. You can see all of the, not only the real data, but the projections are for longer flight segments. What does that mean? It means fewer cities served. It also means larger aircraft. And so these are trends that are underway, have been underway for some time, don't appear to be reversing. The aircraft trend appears to be, the larger aircraft trend appears to be now pretty solidly upward over time. This downward trend was driven largely by the RJs. And those of you who follow the airline world will know that the RJs are all coming out of service, essentially. Not all of them, but nearly all of them. Delta just started a process of removing 1,000 RJs from their fleet. And unless we build more roads will be, this is not my subject, right? We have another speaker to talk about this. But what we do in our modeling is we include road congestion on the average effect of drive speed. So when our agents in the model decide to pick a mode, they do an economic calculation and a bias, also a preference bias calculation, and they pick a mode for trip. If the mode, if their travel is in an area that's highly congested on the highways, they might choose not to drive, but rather to go some other way. Well, enter NextGen, and I'll close with this. NextGen is the nation's investment in the 21st century air transportation system, next generation air transportation system. So the vision for 2025 and beyond includes responding to continued growth of airline traffic. It includes responding to some innovations that they want to understand the effects of in small aircraft, including electric propulsion. Electric propulsion in small aircraft is very intriguing from a technical standpoint and from an economic standpoint. Can it work from a battery energy density standpoint? Well, eventually, yes. And if you project energy density improvements and power density improvements for electrical systems on into the future, in about 10 years, they match current piston engines. Is that good enough? It's better than what we've got. Piston engines are you love them and you hate them, right? I'd love to have a radio, R2800 in my living room. My wife wouldn't quite settle for it. So we also now have these uncrewed aerial systems entering the sea, which have the potential to be game changers in terms of commercial services as well as governmental and public safety operations. One of the big challenges we face here is illustrated in this graphic from one of the central banks. How America works. This is the percentage of workforce in America. This is 0% to 100%. And here's 1800, here's 1900, here's 2000. And what you see here, here's all the people who worked in agriculture back then. No big surprise there, we know all about that. Here's the so-called industrial revolution in the middle here, right? percentage of the population that worked in industry that eventually basically overtook the percentage of the population that worked in agriculture. And then the growth of the service industry. So the question is, what's next? You know, our next epic that defines our economic well-being in the country is not a chapter in our book that's been written yet. We don't know what that next sort of, some people call it the information age, or the age of knowledge, or the age of innovation, and so forth. Not quite clear. Now, you'll read I'm sure you guys are studying robotics, and autonomy, and all kinds of things. People are talking about robots taking over all of our jobs. You're going to get to create all that. I'm going to get to watch. So NextGen itself, I see as a architecture in which we can innovate in air transportation in the 21st century. We need to shift our thinking from just two-dimensional, which dominates most of our, especially local transportation thinking, to three dimensions. We need profitable scheduled air carrier business models. We're seeing that emerge. And we also need commercial on-demand UAS and personal air transportation innovations. NextGen and the airspace innovations, satellite navigation, digital communications instead of analog, trajectory management, like noodles in the sky instead of Vector Airways, and so forth, are the meat of those kinds of innovations. So this may be apocryphal. I haven't been able to actually find the quote by Yogi, but I'm glad to look forward to the conversation and questions.
More intriguing questions than I think we will probably have time for. The next speaker is Michael Pack. He's the director of the Center for Advanced Transportation Technology Laboratory, CAT Center at the University of Maryland. He's going to talk to us about how technology is going to influence things in the highway world.
Thank you. And there we go. So more specifically, I'm going to talk about ITS data is going to be more useful for us in the future for actually making informed decisions about our highway infrastructure, and specifically big data. So a little bit about how transportation departments, especially on the freeway side, have operated in the past. We tend to be really good at buying things. We're good at buying hardware. I'm talking about ITS stuff. Hardware, we're good at collecting data. Maybe not so much with doing anything with it after we collect it, but we're good at collecting it. We're really good at building fancy operation centers, et cetera, et cetera, et cetera. And as a result of all of these different systems that we purchase, we're collecting all sorts of data. Tons and tons of data, more data than most people realize. And as proponents of data at the university level, I get excited about this stuff. And then I go back to the freeway operations engineers and the guys that actually installed the ITS to begin with, and I'm like, wow, you've got all this great data. What are you going to do with it? And they're like, whoa. And they sometimes run away. They don't quite know what to do. They get upset with us for trying to push our agenda on them. And I feel like we've really missed our mark as transportation ITS folks in that we have failed to give due emphasis not just to the data itself, but to how to explore the data, how to visualize the data, and almost most importantly, how to consolidate all these different information sources. Because, again, we're good at installing sensors and collecting data, but they're disparate. They're all over the place. So you might have agency X, whomever they may be. They've gone out and they've created a database for traffic sensor data, and they're collecting tons of traffic sensor data. But then agency Y, who might actually have some of the similar geographic coverage, goes out and then installs other sensors in the same general area and is collecting their own data. They've got their own database, and they're not talking to agency X. Same thing happens with agency Z. And you've got all sorts of other transportation-related data that's out there. It could be accidents, parking, weather, signal systems, computer aided dispatch, transit data, and I've not mentioned air up here or rail, but that could be there as well. And all these data sources are existing in disparate locations, which is unfortunate because as transportation system managers, we should be looking at all the data together and trying to figure out, trying to make good decisions based on all this information. But we tend to be data hoarders. We collect, we save, we keep it for ourselves, we don't share with others. Not good stuff. So this has been a long-standing issue for everyone in the United States and probably other countries as well. And the Washington, D.C. region, at least a number of years ago, decided to try to start to fix this problem. So they hired us at the University of Maryland CAT Laboratory to go out and try to consolidate all these different data sources from all the agencies in the Washington, D.C. region into one centralized repository, one database that then could be used by many. So it could be used by operations folks in real time to manage what's going on out there, make good operational decisions, but also archive that data and use it for researchers and all sorts of analysis and prioritizing projects and all that good stuff. So we've been collecting this data for years and years and years now, and the system has been growing. I'll show you how big it's been growing in a little bit. But our challenge now that we've collected all this data is not to make the same mistakes that have been made before. We need to make this data easily accessible to anyone and everyone who wants to get access to it or needs to get access to it. And in doing so, we don't want to just hand them the data and say, here's the database, go do whatever you want to with it. We want to make it easily accessible. We want to give them tools that make it easy for them to interpret the data and do meaningful things with it. Not just the things we want them to do with it, but the things that they might want to do with the data. So we try at our lab to now build cool tools, essentially, behind these data sets that allow people to analyze it. And so we have this little design monitor that we go along with. But anyway, to me, at this point in time, with the highway systems, we've got this data. It's time to do stuff with it. So I'm going to show you a few screenshots of some examples of tools that we've been building. We are now actually collecting data for a good portion of the United States. See all these roads that are color-coded? Those are color-coded based on speeds and sometimes other data elements as well. But we are tracking millions and millions of vehicles that have GPS installed in them. Some of them are commercial vehicles, fleets, taxi cabs, FedEx, UPS, those types of vehicles. But also if you've got a high-end nav system in your car that's got GPS in it and you're getting real-time data, most likely you're also providing data back to us. Your cell phone, if you have a nav system or you're using Google Maps, you are a probe. You're providing that data to someone, and sometimes we get it. We get copies of it. So we're able to see what's going on throughout the entire U.S. We're pulling in accident data from police systems, computer dispatch systems, from traffic management systems. Zoom in. We're merging weather data in all of this so we can see both real-time weather but also weather forecasts, because weather impacts the highway system, right? Pulling in National Weather Service alerts, National Weather Service radar, road weather systems that have been installed all throughout the country that have little pucks embedded in the pavement. They're telling us what the temperature of the road is, what the surface conditions are like, whether there's enough salt that's been laid down the road, wind speed, visibility, all sorts of stuff, collecting that for most of the U.S. We've even gone out and we've integrated radio scanners from police, fire, EMS, air traffic control, any sort of public safety agency. All these little red guys here is a radio system. You can click on it. You can listen to police, fire, EMS dispatch from almost anywhere in the country. Start to zoom in and get more details. We're pulling in all the typical ITS devices from any agency that's willing to share it with us. So that could be variable message signs, CCTV cameras. We're able to see full motion video, create your own personal media wall and see what's going on. The important thing is that this isn't just for one agency. It's for multiple agencies. So Maryland, D.C., Virginia, North Carolina, everyone's able to see what's going on in, on their neighbor's side of the roadways. Then we try to make all this information I just presented to you on a map much more intuitive. So for every one of those little accident icons that popped up on the screen, that's an accident, right? But just knowing that there's an accident someplace isn't really telling me much about what's going on the roadway or how it's being managed. So we've created this way to go in and analyze all of these accidents and actually see how they're being managed in real time. So we've got this accident timeline that we've created. Imagine this red line right here is the start of an accident at 12:30. That's 1 p.m., 1:30, 2 p.m., 2:30, 2:43 p.m. At this green line, that's when the accident ended. It was over. I've got a tractor-trailer truck and some sort of pickup truck involved. It was raining at the time of the accident. I can see the CCTV, and I can do a map of this. We've got all these little blips that pop up on the screen. Any diamond that you see, that is when an agency was notified about this accident. So, for example, this diamond right here is the tow truck. We can see it was notified at 1:05 p.m. The dashed line that follows is when the tow truck was driving to the scene of the accident. Took it about an hour and 12 minutes to arrive. Hopefully you weren't in this accident. And then the solid line that follows is when it was actually on the scene doing something, right? So taking all this data and turning it into a picture to show you what's going on. We do the same thing for the fire department, the police, safety service patrols. There's a medevac helicopter that was called to the scene. And below this, we have the lanes. And this is essentially the lane status over time. When the accident first started, right lane and right shoulder were blocked. It was on the side of the road. Then, all of a sudden, what happens? Fire department, the police arrive on the scene. They shut down the whole road in the northbound direction. Keep going forward in time. That's not a shocker for most of us. Keep going forward in time, and all of a sudden, the southbound lanes get closed. Why? You look up top, there's a medevac helicopter that lands on the scene. The lanes have to stay closed while the medevac helicopter lands. Medevac departs, all the lanes open, well, a few lanes open, until this accident investigator finishes doing whatever they're doing, and then all the lanes open up except for one on the shoulder. Further below this, minimize this guy, we're showing you what's going on the roadway while the lanes are blocked. So this line right here, that's the location of the accident. 5, 10, 15, 20 miles behind the accident, traffic's flowing down this way towards it. The red is the queue that's backing up behind the accident over time. You put your mouse over it, it's interactive, tells you the speed and the distance. You can see that after, or when the lanes open at about 12:43 p.m., the queue has backed up about 9 miles, and you can see that the queue continues to back up about 45 minutes to an hour after the accident while the queue starts to dissipate. So we're taking all of these disparate data sources that we're getting from all these different databases, consolidating it together, creating a picture of what's going on. This is a real accident. We can create this for the majority of the incidents that we get in the databases that we're collecting. So in addition to this type of information, we're also pulling in all sorts of sensor data, so you can do your typical engineering analysis of sensors. We're pulling in evacuation data. We know where all the staging areas are in case you have an evacuation, and aerial photography of where you could put people and goods in case something bad happens. We have hospitals and beds. We know how many beds are available in the hospitals in some regions in real time. Traffic control points. We can tell you which intersections need to be blocked off or managed in a certain way in case there is some sort of an incident. We have transit data. So you can see where the rail cars are moving, whether they're on time. In some cases, we can even tell how many people are on board a train or a bus to tell you if it's at capacity. Way stations. We've got a number of way stations that we're pulling in data from, and every time a vehicle drives past this location, this is a virtual way station, this way in motion, we're taking a picture of the vehicle, we're building license plate recognition in so you can see who it is, and we're measuring the axle spacing, the axle weight of every single vehicle that goes by, and if it's in violation, things turn red, we tell you which axles are overweight, and then a police officer can decide whether or not they want to pull this guy over and do an inspection, so on and so forth. So we've got all this great data now. We've got some visualizations that allow you to see what's going on in real time. The question is this good enough? Does this really give you enough situational awareness to be able to do a better job of managing the roadways? In some cases, yes. In other cases, these charts and graphs telling me there's 500 vehicles per hour moving down the roadway, maybe that doesn't really mean so much to certain folks. So what we've done is we've gone out and we've hired a lot of students who want to be video game programmers. And they've come to our lab and they've found a way to take this real-time data that we're getting from all these different systems, merge it with geospatial data sets that give us terrain and elevation, and you can take a game controller and you can fly around virtual cities, real cities that are modeled. We're animating traffic in real time based on the sensor data that we're getting, showing you where the queues are backing up on the road, showing you what the breakdown of classification of vehicles is on the roadway. You can fly past your infrastructure and inspect it virtually and see what's going on. You can interact with your sensors, see what they're telling you, just like you would with the two-dimensional version. Color code the roads, tell you what's going on. As you fly past your CCTV cameras, we can show you the live CCTV image so you can inspect what we're animating with with what's actually happening out there. Do the same thing with the transit and the rail information. We've got buildings modeled so you can see where all the landmarks are. Helps the operators get a sense of where they're actually at. Terrain is built in so you can actually fly through the Grand Canyon or fly next to rivers and mountains. All the weather data is built in, and when you fly into an area where it's raining, you actually see the rain fall down at the appropriate volume. Same thing with the snow, but it doesn't build up on the ground. So we call this a virtual helicopter. It's a way to actually allow the operators to pretend like they're in their own traffic copter. They can fly around and see what's going on. It's fun stuff. So now that we've got all this data, we're archiving it. We're archiving it indefinitely. There's all sorts of cool tools that allow you to go in and generate heat maps of where accidents are occurring, do additional analysis to do clustering to see how many accidents are occurring on in each geographic region. All these are web-based tools, so anyone in this room can get access to these and play around with them. But we've got this new set of tools that we're particularly proud of that's allowing the DOTs to now go in and do a better job of prioritizing their projects for the state. So imagine being able to go into a system, click a few buttons on a website, and ask, hey, North Carolina, can you tell me where the worst congested locations are in my entire state? Based on all this detector data, all the sensor data, all the probe data that we've got. So, I actually ran this query a few minutes before the session started. I actually asked our system to tell us the worst congested location between March 1st and yesterday on the interstates. They came back with a ranked list. Each of these guys is a serious bottleneck, serious congested location in North Carolina. The worst location, according to this data, seems to be I-85 South at West Mallard Creek Church Road. That seems to be in in the Charlotte region. The average duration of this bottleneck that occurs is 3 hours and 37 minutes. The average maximum queue that it gets to is 11 miles. It occurred 52 times between March 1st and April 8th. And we can see the stats for all the other bottlenecks. But then, if you look down in the lower right-hand corner, there's this weird spiral graph, color thingamajigger. So this is a 24-hour clock. Innermost revolution would be March 1st, then March 2nd, March 3rd, until we get out to the last revolution, that's April 18th. Anytime there's color that appears on the screen, that's when that location was congested. So we can see that this particular bottleneck is primarily occurring in the morning between about 6:30 and 10:30 a.m., and it occasionally occurs in the afternoon, but it seems to last forever in the afternoon. I don't know why. And we can scroll down and look at some of the other congested locations. This one only occurs in the afternoon. That one's primarily in the morning again. That one's only in the afternoon, so that's afternoon rush hour. I don't know anything about the roads in North Carolina, so I don't know if these are crazy locations or not. But anyway, with just a few clicks now, you can pull all this information down at your fingertips and start to do a better job of prioritizing congestion. we've taken it one step further now, and we can take that congestion information and we can turn it into dollars. So tell me how much money we're wasting because we're sitting in that congestion. We're late to work. We're late to get home to pick up our kids from daycare. We're burning fuel because we're idling. And we can create tables that tell you by hour of day and by day of the week how many thousands of dollars you're wasting in these bottleneck locations. It's cool stuff. So I know I only have a couple more minutes, so I'm going to move on to something completely different. We're trying to do visualization work to help improve first responder safety. So we're trying to take visualizations to help improve the way first responders respond to accidents on the roadway. A safe way to teach them how to respond to accidents. Incident management training right now is very expensive. It's usually done out in fields and mock scenarios. You might crash some cars in one another in a field and have pretend victims lay on the ground. The first responders will come up and they'll do whatever it is they do to the victims. They don't really get to practice traffic management, traffic control, scene safety as well as we'd like. So what we've done is we've gone in and we have created a massively multiplayer video game
Dispatch, police hero.
that allows all the responders to log in to this virtual world, and we can have firefighters, police officers, traffic management personnel. They can walk around on the roadways. They can set up traffic control and see how that affects the queues and incident management. We've got towing and recovery people that can drive around and park their vehicles in a appropriate pinned-off position. We have victims that can be injured. We have fires that can break out, and the firefighters have to deal with the fire, all while handling the traffic that's going on the roadway, being safe, putting on personal protective equipment, so on and so forth. It's very, very cool, and it's being used by a good number of first responders on the East Coast. I think we've actually done a training scenario in North Carolina as well. So the power behind this is that we're actually recording every single action that any of the first responders does while they're playing the game. After they finish playing the game, we can create that timeline that I showed you earlier based on how well they responded to traffic, and then you can click on any point in the timeline and it transports everyone in the game back to that point in time, and they can watch themselves and they can see how well they communicated with one another and how well they managed the incident. So that's it. My concluding thoughts are really just that there's a world of data that's available to us now that we probably don't know about because it's been difficult to get to in the past. Data's coming along. We're collecting about 1 billion records every day now from the U.S. system. And my vision of the future for the highway system is getting this data out there to more people, creating more tools that allow us to do better analysis and make better decisions based on real data. And thank you.
We have a few minutes for questions and answers. Love to have some questions from the audience. Yes, Mark.
For your rail safety slide, when we were making, before we bottomed out, what were the attributes that was attributed to in terms of how we were able to?
How we got there?
Yeah.
Primarily automatic warning is a great process. So replacing the crosswalks with active ones and primarily what's there. And there's been a tremendous investment in Section 131.
Yes, in the back.
Questions for David. Can you explain a little bit more about what you're looking for as far as an ability to measure rail compression, and also what kind of technologies you're currently using to do that?
Okay, we're talking about preventing track buckles here. We like to lay rail at a certain temperature, and that's usually somewhere around 100 to 110 degrees. So obviously we have issues with curb sucking, seasonally, or maintenance forces and long too much rail out, that compressive balance gets out of whack. So The best technology we use today is really what I call bandwidth string. We actually it came from the UK, and we attach about 70 foot of it, and we jack it and we measure resistance. Okay. We're also looking at vibration technology. We're looking at ultrasonic technology, but that has not been proven yet. What we really want to do, all those are fixed. What we really want to do is run down the track at 60, 70 miles per hour, maybe even under a locomotive and measure it.
Thank you. Yes, Ed.
Mr. Connell, this is for you too. First of all, let me thank each of you on the panel. Very interesting presentations. You put up on one of your slides that the railroads are exploring the LNG conversion from diesel. Are any of your railroads, any of our nation's railroads, looking at all at hydrogen-powered locomotives?
There's been a lot of small-scale work over the last 10 years. It does not have a lot of traction right now, but obviously it's in the back of everybody's mind. So that's about the best answer I can give you right now. Yeah.
There is a fellow who's here in Morrisville who's a promoter of that technology. Yes?
For Michael Pack, on the data you're talking about, how real time is the access to that data, or is the data when you access it, and what tools and methods are available to access it?
So every agency that provides data has a different latency. Some agencies, you're talking milliseconds. So the second they get the data from their sensor, type something in, it's at our fingertips. The probe data that covers the entire U.S., we get that every minute. And so you can expect some latency there, but a minute or two. I think the worst we have is around 5-minute latency. But when it comes to getting access to the data, if you are doing research on behalf of a DOT, or you are a DOT yourself, or a public safety agency, you can get free access to almost all of that data through ritis.org, and there's a little request an account button. You click on it, you fill out your information, and it takes us a few days to verify you're legit, but you get access to most of it. There's a few proprietary data sources that we have to get data use agreements.
Other question? Yes.
Question for Michael Pack. Are you trying to expand the detector tool from, I know that you have been flourished a lot in recent years from DC to Florida and to California. Are you planning to do it nationwide detector static?
So our goal is to have these tools be available for the entire U.S. We feel that a tremendous, apart from the operations benefits of having access to all this data, we feel that a tremendous amount of research dollars are being wasted on trying to find data, trying to format data so that you can then start to research something and answer a question. We want to have all the data as a national resource that is just there so that we can use more of our research dollars to actually solve problems instead of finding data. But we're at the mercy of the agencies to give us their data.
Jim, you had a question.
Question is for Bruce. You talked a lot about commercial air service. And my question is, when am I going to be able to get on a FedEx plane and take it from Greensboro to Memphis and call that a good passenger trip for me?
I've got some people I can give you contact information at FedEx who can vote. Well, let me say a little bit about that.
I just wonder if that's part of the future.
I think that I can't say that a company like FedEx or UPS in particular has any imagination about people carrying people. But they both have been engaged in studies that NASA has undertaken in the JPDO, which is JPDO is the Joint Planning and Development Office for NextGen in Washington, multi-agency office. It's all of the agencies that touch aviation, of which there are a dozen, are involved, and they there have been studies with the FedEx and UPS folks looking at autonomy of aircraft and what it could mean for reducing operating costs. The classical rule is your OpEx was one-third crew, one-third of the aircraft, one-third fuel. Fuel prices have driven that up to about 40, 45%. The other parts left to the crew, the CapEx, but the essentially cost of money. There is some interest in none of those carriers, package carriers, cargo carriers, have made any sort of publicly available about what they are thinking about in that arena at this stage. However, the technology in the airspace and the technology in the aircraft are coming along sufficiently well that we meaning the teams that we participate in government studies are modeling the requirements of the airspace for that kind of operating capability within about 20 years or so.
That's how David smiles, so I assume that UP's getting ready to start transporting people too. We stopped that model back in about 1971.
That's right. That's right.
Yeah, Bruce, I had a question about, you mentioned this airlines getting rid of the regional jets. Do you see still the hub and spoke model continuing into the future, or that's also going to disappear?
It is turning out that, for those of you who have an interest in understanding airline economics and air carrier operations, you'll want to spend a little bit of time in the field of network science and complexity science. So the question you're asking is kind of what the future of the networks are, right? So there are two fundamental kinds of networks: the random networks, and then there are small world networks, and they're very different in their performance economically. Southwest Airlines, the most successful airline in the history of aviation, practices very much a small world network design and operation, along with many other features of their business model. The so-called legacy air carriers, the Uniteds and Deltas and the others, Americans, practice random networks. The random networks, the hub and spoke system is a random network. It's not designed for economic performance in the same fashion that small world networks are. I know I'm using some language that's a little bit obtuse or whatever the right word is. Forgive me. But it's a great question, and it's a great field of research.
We have time for one more question. In the back.
Questions for Dave. All the different technology you described about operations and maintenance for the freight railroads, and just trying to get more and more safety, more capacity, more operational efficiency. How, if in any way, does that impact the use of the railroads for the higher speed rail, the passenger rail piece? I mean, at some level, it seems like the freight rail is going at a certain speed, and then the passenger rail wants to go at a different speed, so there's a natural disconnect between that. Are there elements in technology or some other things that would make it so some of the passenger could become more likely, or is this just fundamentally an economic/technological disconnect that won't be resolved?
Well, I think you're accurate to observe that obviously trains that are running different speeds consumes a lot more capacity than trains that are running at the same speed. We even see that with our freight network. We run our premium product at 70 mile per hour, some of our product at 40 mile per hour. We're demonstrating, I don't know the answer yet. We are demonstrating right now a higher speed segment between Chicago and St. Louis with IDOT. We are certainly happy to have the discussion anywhere about passenger rail being on our network, provided that our long-term capacity is made whole. I'm not sure that we've got models smart enough yet to understand really what that looks like, but it's a learn as you go here. We don't see it being feasible for anything higher than 110 is how UP looks at it. I think that's how most of the Class 1s look at it, and that only makes sense, we believe, right now in certain segments where the ratio of passenger to freight is under probably 10 or 20%.
We could go on for a long time, but I'm looking at a clock that says it's 7:30, and I know that there are some other things that we need to do today, so I think we should thank our guests. Thank you very much, Mary. Monty, back to you.
Yes, thank you. Yes. Is she aware that we are?
I texted her now. Trying to preempt another call.
Okay, here she is.
We'll call you. There she is.
All right. Thank you, George, for an excellent job moderating the panel. Thank you to the panelists. I want to conclude our meeting today with the announcement of the CE EdVic Transportation Founders Fund Graduate Scholarship. I want to invite Stacy Phillips from Kimley Horn and Associate, who is representing the EdVic family. As you know, last year we renamed the scholarship after the late EdVic, who was, as you know, a long-time supporter of NC State, of our transportation program, and also a long-term member of the ITRI Advisory Council. And Ed would be very pleased with the selection this year. I'm delighted to announce that our technology works. Hi, Shannon.
Hello.
Shannon Warhol is soon to be graduate from the Civil Engineering Department at Notre Dame University, is this year award recipient. She has maintained a 3.8 out of 4 GPA while completing a minor in Chinese, and is committed to enroll in our graduate program this fall. Her research interests are in the area of interchange design, particularly those new innovative designs that may be posing challenge to driver and engineer. Believe it or not, Shannon has amassed an incredible long record of achievement at Notre Dame. She's been on the Dean's List for the past 5 semesters. She's a member of the Engineering Scholars Program. She's won the Hugh O'Brien Young Leadership Award. She is the Civil Engineering Class of 2013 representative on the Engineering Honors Board, was president of the Joint Engineering Council, and the list goes on and on. Needless to say, we here at NC State are very excited at having Shannon join our program this fall. And on behalf of the TFF Executive Committee, I'm pleased to offer you the check. What is the check? Big check. The big check. This is the real check is in the mail. In the amount of $3,000 in support of your graduate work at NC State. Congratulations, Shannon. If you want to say something, go ahead.
Yes, thank you so much. I really appreciate. I was out at North Carolina, or NC State, sorry, I'm still getting used to the terminology. I was out at NC State a couple weeks ago now. I really loved it out there. So I'm very excited to join you all in the fall. And thank you so much again for the scholarship. I greatly appreciate it.
Thank you. Thank you very much. Thank you, Stacy. Jim, Saul, what is that?
Okay.
I have the little mementos. Here we go.
Yeah, let's hand these things out.
Yes. We have 2 mementos for our panelists. Thank you so much. Bruce, thank you.
Thank you.
Michael, thank you so much.
All right, we want to thank everybody again for coming out this evening. We hope you enjoyed the program like we did. Certainly the speakers will be around a little bit afterwards if you had other follow-up questions. Again, let's give Nagy and the folks here at ITRI a big hand.